So like I was saying, that this is the non-equilibrium part of the course. So all of these systems, we're going to be calculating how fast they want to go towards equilibrium. And any kind of change in a system like that is called flux. So this is a whole section of engineering called material or transport. It's material or heat or energy or momentum transport. Now, before we get into some of those transport systems, let's talk about the most common non-equilibrium system that we deal with on a daily basis, and that would be electrochemical cells or batteries. And then hopefully if we get to it at the very end of this part, we're going to talk about fuel cells. So this is non-equilibrium electrochemistry, where we deal with batteries, corrosion, and all kinds of things. Corrosion really is probably the number one thing we spend our money on after something's made, is trying to prevent corrosion. But in terms of batteries, the storage of electricity, this is an area of research. This is a very active area of research. So this thing that makes our batteries go is this idea of electrical potential, and it's related to delta G. So this is an equation that you should just, have ingrained in your mind, because look at what this does. This is available. We're very good at calculating delta G with our reactions. We can go and do reactants minus products and look at delta G, but now we can get the electrical potential out of that. So that's what E is. E is the electrical potential. F is Faraday's constant. And Faraday's constant has a couple of different forms. It could be coulombs per mole, or it could also be joules per volt mole. Okay. And so this is a way to use it to turn that joules per mole in the delta G into volts. And of course, in this equation, we're using Q, which is our reaction quotient. It's not K. If it were K, we'd be at equilibrium. And so a battery at equilibrium has 0 volts electrical potential. Okay, so we want this to be not at equilibrium. We want it to be far from equilibrium so that it's pushing electrons through the circuit. So it's this whole tendency towards equilibrium that's driving electrons through our circuit. And so these subscripts or superscript 0 means at 25C and 1 molar solutions. So that would be the standard Gibbs energy. If we substitute in that NFE, then we have a standard potential that's corresponding to the standard Gibbs energy. So we could calculate the standard Gibbs energy using our tables. That would give us the standard cell potential. Then we could put in other concentrations in for Q, and we could have some adjustment to that standard potential, and we would get the actual potential of that cell. The thing that people mess up most of the time is that, notice the minus sign in front of NFE. So what does that tell us about spontaneous potentials? If spontaneous Gibbs energy is negative for a reaction, the spontaneous potentials are positive. So if you have a positive potential for a cell, then that's spontaneous. So be sure to write that down. If you have a positive potential for a cell, that's a spontaneous electrochemical cell. And so we could rearrange, we could divide everything by NF, and so we end up with this RT over NF ln Q. And you can see this as a correction. You have the standard cell potential and some correction term based on the actual concentrations of your various components, and that gives you the actual cell potential. So this is what you probably saw in the freshman chemistry is the Nernst equation. So if we put in room temperature for temperature, then we end up with this constant at 0.02569 volts. And then you have the number of moles. Now, what is the number of moles in this case? We'll see that later when we balance the reactions. It's the number of electrons transferred. Okay, now the Nernst equation is typically written in the natural log form. And so when you convert this over to, base 10 log, then you end up with this constant of 0.05917. And that's given to you in this, I think, Chem 2 when you do these calculations. But I'm not sure that in Chem 2 they explain where the 0.05917 came from. And so that's where it comes from. It's RT over F converted to log base 10. So let's look at some examples. And so if all of these concentrations have been 1 molar, then if they're not 1 molar, we use Le Chatelier's principle to predict the cell potential. So here's a standard redox reaction of aluminum and manganese. And if you've got these aqueous solutions here, those are the ones that we're talking about being at 1 molar concentration. So in this case, it's only the aqueous species that we're talking about being at 1 molar concentration. And then those concentrations are going to be raised to like the 2nd power or the 3rd power. And in our reaction quotients and in our equilibrium constants, solids and pure liquids don't show up. So these don't play a role. They play a role in the reaction, but they don't play a role in Q or K. So we're really just looking at the aqueous concentrations, the things that can change their concentration. And this is the standard cell potential. So this is the potential that this cell will produce with 1 molar concentrations. So that's how hard the cell pushes. That's the potential. Think about the word potential. When you have a ball on a hill, you have potential energy. If it's higher on the hill, you have more potential. So this electromotive force, this cell potential, is how hard this is pushing on the electrons. Okay, and that's how hard it'll push them through your circuit. So potential is a great word. So if we put the aluminum concentration at 2 moles per liter, but we keep the manganese at 1 mole per liter, then the actual cell will be greater than or less than the standard cell. So look at this reaction. What are we adding? We're going above 1 molar on the products. So will that make it more spontaneous or less? So we're working on Le Chatelier's principle. So we're putting pressure on the system. It's not at equilibrium, but we're trying to determine if it pushes harder or less hard. Less hard because why? It's got too many products for that cell potential, and so it's going to be harder to push forward. And so it will be less than. So correct. What if we do the opposite? What if we make the manganese 2 molar and the aluminum 1 molar? So if it pushed with a potential of 0.48 with 1 mole on each side, and we create more reactants, it's able to push harder. So it'll be a higher potential. That should make sense to you. Just thinking about Le Chatelier's principle, although we typically thought of Le Chatelier's principle as dealing with equilibrium situations, this is not at equilibrium, but we're trying to say like how steep is the hill. If we have more reactants, the hill's a little steeper, okay? And if less reactants, more products, then it's not pushing as hard, and it has less potential. So we always use those Ks. And we could calculate the actual change if we have that 0.48. We put that in here. Find my pen. There it is. 0.48 goes here. And we might put like 2 molar here and 1 molar there. And we could calculate the actual potential. So we could use this Nernst equation to calculate those things. So here's the example. I did an even more extreme example. I made the aluminum 0.001 molar and the manganese 2 molar. So we can put in those numbers. And also I need to know the number of electrons transferred. So if we're looking at this, I've got +6 charges here on the manganese that completely go away. So I got 6 electrons from the aluminum. And that's 2 times 3, right? So the aluminum gave up 6 electrons to become 2 aluminum 3+ ions, and the manganese grabbed 6 electrons to be 3 manganese metal ions or metals. So we can put that 6 down here in the denominator. So this is the 6 here. That's the number of electrons, 6 moles of electrons. So then calculating that correction factor, you see it seems like a pretty dramatic effect. 2 molar on the products above 1 molar, and then almost no products, 2 molar on the reactants. And even then, the correction is pretty small. So the concentration corrections are pretty small. You'd have to have extreme concentration differences to get a decent voltage out of it. So most of it's governed by the cell potential, the standard cell potential. Okay. Now, as the galvanic cell reaches equilibrium, then that cell potential will equal 0. And that's why a battery goes dead. So you could completely fool people who don't know anything by selling them very safe, pre-equilibrated batteries. So they're dead batteries, but they're safe, right? They're not going to cause fires or anything like that. They won't be worth anything. So in these spontaneous oxidation reduction reactions, these electrons are transferred and energy is released, and maybe we could work to get that electron potential to go through our circuit. And so that's what we've done. We separate the 2 electrodes. We make the electrons go through the outer circuit and the ions go through the solution, and that's a galvanic cell or voltaic cell. So here's a little scheme of what's going on in a copper zinc cell. So notice that there's transfer of electrons, but there's also transfer of ions. And so the negative values go one direction, the positive values go the opposite direction. So up here we have the electrons going through our circuit. This voltmeter is testing how hard they push. So it's measuring the potential. And so this particular pairing of zinc and copper will give 1.1 volts of standard potential. Notice that this is copper nitrate and zinc nitrate. And so if we didn't have this connection in the middle, this bridge, then there would be no push power. It actually has to be a completed circuit. And so notice the negative anions here are flowing in the direction. So the negative charges are going in a clockwise manner through this whole circuit. And the positive ions are going in the opposite direction. So sodium's coming out of the salt bridge and going into solution to replace the missing copper ions. So copper is plating out on this copper electrode spontaneously. So we're going from copper 2+ to copper solid. And so that's what's happening here. Copper 2+ is going to copper solid and chewing up or absorbing 2 electrons. That's why this electrode is positive, because the copper is chewing up those electrons. So it's deficient in electrons and it wants them. And so you put a wire on there connected to the zinc and it pulls those electrons from the zinc electrode. When those electrons are pulled off of the zinc electrode here, then the zinc metal out here on the outer edges of this electrode becomes zinc 2+. It's lost its electrons. That's water soluble, so it goes into solution. And so then eventually some of this zinc migrates into this salt bridge to replace the sodium that's missing, that replace the copper that's missing. And so the cations have to be conducted as well. And in almost every case, it's the cation conduction that slows the battery down. We cannot push electrons any faster than we can conduct the cations. So that's a real problem. So over here on this, the zinc side, the zinc lost electrons, and so that was the oxidation reaction. So this zinc gave up 2 of its electrons and became zinc 2+, and those 2 electrons went through the circuit, came over here to the copper, combined with the copper cations and made copper solid. So here we have this reduction cell potentials. We'll see a table here in a minute of the reduction cell potential table. and it has all of the reactions written as reductions. And so for the oxidation reaction, you have to flip that reaction to make it an oxidation, and then you have to change the sign on the reduction reaction that takes place at the anode. Let me go back here and show you. This is the zinc anode, and the anode is where oxidation takes place. And here's the cathode where reduction takes place. And if you think about the names of the ions, where is the copper 2+ ion going? Where is it attracted? It's attracted to the cathode. And so that's where the name cation came from. The cations are attracted to the cathode, and the anions are attracted towards the anode. So the nitrate ions are going that direction. They're going towards the anode, so they're anions, and the cations are going towards the cathode because they're cations. So if you never knew that, we're finally there to answer that question that you didn't even know you had. Okay. Now I've got a nice little memory trick here because there's lots of little pairwise things that can get mixed up. And these are simple concepts, but if you get them mixed up, you're wrong and you lose points, right? So this is my memory trick. If we have a galvanic cell, the electrodes go down into the solutions. Okay? And so you can only put the anode on the word oxidation because the word oxidation has an A in it. Isn't that cool? I'm very excited about this memory trick. I came up with it. Okay, and the reduction doesn't have an A in it, so you cannot put the anion on the word reduction. But it does have a C, so you can put cathode on that word. So these cathode and anode dip down into the solutions, and then the process that happens at that electrode is reduction or oxidation. And so you can't get them mixed up if you think of them this way. So the anode attaches to oxidation, the cathode attaches to reduction. I even color-coded them for you. Okay. So this is the potential table that I was telling you about. They're not always sorted in the literature. Okay, so if you look at the literature, that's one of the first things you want to see. Are they alphabetical or are they sorted by reduction potential? Okay, if they're alphabetical, then you're just going to have to look for the species involved and find them, and that's nice, it's convenient. Okay, but if you sort them by reduction potential, there's a little more information you can get out of it. Because up here, this is the highest reduction potential on this table. And down here's the lowest, it's the most negative. Now remember when we focused on, oh my goodness, somehow I got a yellow pen. Okay, so remember when we were looking at the thermodynamics tables, we said that we needed a reference state. And so for the enthalpy of formation and the Gibbs energy of formation, what was the reference state for those tables? A little bit of review. So you've got chemical reactions that always happen pairwise. And in order to make a table of the individual components, you need something that's going to be your reference material. So like if you have a substance that you react everything with this substance, and it's maybe exothermic or endothermic. And so then you can rank all of them relative to that substance. Okay. And so we've decided for thermodynamics, for formation and enthalpies and Gibbs energies, there were a set of substances that we defined as our reference point. So we set them at 0. And then everything else can be ranked above or below those things. What were the reference states for what was 0 in the enthalpy and Gibbs energy of formation tables? Elements in their standard states at 1 bar and room temperature, I believe. Yeah, 1 bar room temperature. So like oxygen O2, so that was that form of oxygen, O2, gas. 1 atmosphere, room temperature, or 1 bar room temperature, oxygen's a gas. If I had oxygen, O2, liquid, that's not its standard state. So that's not 0. And if I had oxygen atom, that's not the natural form of oxygen at 1 bar at room temperature. So that's not at 0. But O2 gas is. So we need that 0 point so we can rank things above and below. Same thing with electrical potentials. We have things that are reacting with each other. How do we get each individual thing? Now, think about the reaction. We have these two things reacting with each other. And I want to just talk about one of them. So how do I rank the individual components? I need to find a reference state. So we've defined the reference state as this, as hydrogen. So turning hydrogen ions into hydrogen gas, which again is an element in its standard state. So this is our reference state right here, and it's defined as 0 volts. So if we think of potential as altitude, right? What is sea level? Sea level is hydrogen, right? So if we're going to climb a mountain, we're climbing that mountain and the altitude is relative to sea level. We could go below sea level and those would be negative potentials here. So we could still have negative potentials, things below sea level. So that's what we've done with this electrical potential table, and the reduction of hydrogen ions. So acid protons, the reduction of those making hydrogen gas is defined as 0. It's kind of a tricky electrode. You have acid solution and hydrogen gas bubbling, and you measure the potential across that little glass electrode surface. But anyway, what I'd like to show you though is when we make a cell, we're pairing up these things. We're pairing up the reactions. And so looking at this forward reaction, so cations grabbing electrons being reduced to make hydrogen gas, and putting that in contact with any of these metals. If I run any of these metals backwards, I change the sign on the reduction potential number and add them together, and that's going to be a positive number. You see that? So I'll have 0 for this. This will be 0 minus a negative number. Okay. And so that's definitely going to be positive. So all of those cell potentials are going to be positive. They're all going to be spontaneous. So if I put any of these metals, this is a practical application. If I put nickel or iron or zinc or aluminum or sodium or lithium in acid, what's going to happen? Those metals are going to turn to cations, and the acid protons are going to turn to hydrogen gas, and I'm going to see bubbles. That's a bad situation because I'm producing hydrogen gas. And if it's an iron container, I'm chewing through my container. So don't store acid in an iron container. Not only will it chew through the iron, it'll also produce hydrogen gas, which is not good, okay, in terms of a confined space, explosive atmosphere, and so on. The other practical application is, notice how I would say clockwise, pairwise, or clockwise connections in this table are spontaneous. Because even if I'm up here, if I have this reaction, let's take this permanganate here. If we put that in contact with chloride ions, okay, so this top reaction goes forward, this bottom reaction goes backwards, and I have 1.51 minus 1.36, okay? It's greater than 0. It's positive. So it's a positive cell potential. You see how that's a clockwise pairing of two reactions in this table? The top one goes to the right, the bottom one goes to the left, and I end up with a positive cell potential. So clockwise pairings, when the table is sorted high to low, clockwise pairings are spontaneous. We use this in my research group to plate metals. And so we're taking aluminum metal here and we're putting it in a solution of zinc ions. And we're plating zinc ions onto the surface of the aluminum. And then we're putting that in solution with nickel, and the nickel dissolves off the zinc and gives us a nickel coating. And we don't even need electrodes to do this. We can just put the aluminum in, coat it with zinc, that dissolves off the oxide layer, and then we put it in nickel, and we plate nickel onto aluminum. So a nickel surface is less reactive, and so it's going to be a better coating for that aluminum. So let's talk about balancing redox reactions. A lot of them are real easy to balance, like this. If we just have zinc and hydrogen ions producing zinc 2 plus and H2 gas, we can look at this and we can say, well, I ended up with H2, so I need 2 hydrogen ions. And then we look to see if the charge is balanced. And I have 2 plus on the left and 2 plus on the right, so we're good. Everything's balanced. And I know that N is 2, the number of electrons transferred is 2. So this is the easy case. Other redox reactions are not so easy. There's a procedure that you have to follow to balance them. So let's look at those. Okay, so balancing these redox reactions, we do it in 2 separate processes. We pull this reaction apart into half reactions, and then we balance each half reaction independently and then combine them. So if you follow these steps in order, it's easy. And I think it's way more fun than Sudoku. Okay, so here's the rules that you follow. I mean, Sudoku's dumb, right? Any 1 through 9 in a column or in a row or in a little square, and it's okay, but it's the same question over and over again, right? This is much more interesting. The elements first that are not oxygen or hydrogen, okay, which is each balancing half reaction. You balance the elements other than hydrogen and oxygen first. Then we balance oxygen. Now, this is the tricky part of the puzzle. We don't just put oxygen on one side or O2. We balance it using waters, because in these reactions are aqueous reactions, and so water will provide the oxygen if we need a change in oxygen. Okay. And then hydrogen, we don't balance hydrogen with H2, we balance it with acid protons. Now, not every reaction is facilitated by acid. Some react in a basic situation, but we'll know that at the end. If our acid protons show up as products when everything cancels, then we know that that reaction would move forward if we put it in base, because it's producing acid protons, and if we put it in base, it'll suck those acid protons out and it'll drive the reaction forward. But in terms of keeping things simple, let's balance everything using acid protons. That's very simple to do, and then we can make it a base later. And then we can't forget the charge. So we need to balance the charge on the left and right, and the only way we can balance charge in redox reactions is using electrons. And electrons are negative. So you got to look to see which side has the highest positive charge that you want to bring down, and that's the side you put the electrons on. And then we have 2 balanced half reactions, and they have to shake hands. So if one reaction produces 3 electrons and the other reaction needs 5, then we're really in a situation where we got to raise it up to 15. So we got to multiply the reaction that gives 3 electrons by 5 and the one that requires 5 by 3. And so the handshaking is 15 electrons. Then we add those down and subtract things that appear on both sides. So let's learn by doing. Here's an example. So this is a great titration, a redox titration. And I love this titration because the permanganate acts as its own indicator too. So it's just a nice, clever way to determine how much oxidizable material is in a solution. You could do this. We could do this at East Palestine when they had that spill and the train wreck and everything, and you got contaminated water. You could take that creek water and you could titrate it with permanganate and see how much organic chemical load is in the water. Okay, you put the oxidant in there, and if there's organic molecules that get chewed up, the permanganate's color goes away until it doesn't. And when it doesn't, there's no more organic molecules in there that it's eating up. And so this is an example of titrating oxalate, this diacid with permanganate. So we have oxalate in solution and permanganate in solution. We mix them and we make CO2 and manganese 2 plus. So I guess the first step is to see what the half reactions are going to be, and hopefully it's obvious. Like in this case, I think it's obvious. You have manganese on both sides, and you have the carbon on both sides. So we're going to make a carbon half reaction and a manganese half reaction. Now, some reactions are what they call disproportionation, and so trying to think of an example. if we come across an example, I'll point it out. But most of the time, it's pretty obvious that you have these two half reactions. So here's the carbon half reaction, the oxalate ion going to CO2. So the first step is make the half reaction. Second step is balance all elements other than oxygen and hydrogen. So we got to balance the carbons. So we got to move a coefficient of 2 over there onto the CO2. So the carbons are balanced. And notice why we do these in order, because that changed the amount of oxygens. So we're going to hold the oxygens off until after we get the carbons balanced. Now we balance the oxygen, and it is balanced, so we got lucky there. Okay, 2 times 2 is 4. And then we balance the charge. So we don't have any hydrogens, and so we didn't need to add any acid protons. So to balance the charge, we need to add 2 electrons on the right side. So it's that they have to be equal, not that they have to equal 0. Because if they had to equal 0, we'd be stuck. We cannot get a -2 any closer to 0 if all we can give is negative things. Okay, so we've got to make the left side equal the right side, not everything equals 0. Okay, so we put 2 electrons on the right, and now our charges are balanced. And so we can check that. One way to check that, we can just look at it and say, okay, I've got, the two carbons. Let's go here. 2 carbons, 4 oxygens, 2 times 2 is 4, and then I've got the 2 minus here equals the 2 minus here. So everything's equal, we're good. Okay, the manganese, that's the half reaction, and the manganese is balanced, so we do the oxygens next, and we have to add 4 waters on the right. So we put the 4 waters there. That is brought in hydrogens that didn't exist before. So now we have to do something with acid protons. So 4 times 2 is 8. So we add 8 protons on the left so that the hydrogens are on both sides. And that changes the charges. So that's why we hold the charges off till last. And so we add 5 electrons to the left side. Why is that? Well, on the right, we have a 2 plus. Okay. So here's our 2 plus. So we have 2 plus here, and then we've got 1 minus here, let's see, and 8 plus here. Okay, so 8 minus 1 is 7 on the left, so why don't we add 7 electrons? Because we're not trying to get down to 0, we're just trying to get down to 2. Okay, so that's why we only add 5 electrons. So we add 5 electrons on the left, and now everything balances out. Minus 5 plus 8 minus 1 is equal to plus 2. And then we can check the atoms, 8 hydrogens on both sides, 1 manganese, 4 oxygens. So everything checks out. I like these because you can check your work. So then we combine the half reactions. So the oxalate produced 2 electrons, and the permanganate needs 5 electrons. That's a strong oxidizing agent. It'll steal 5 electrons from something. And so we multiply one by 2 and the other by 5 and bring it down. And that's where I think people make their mistakes. They'll multiply the oxalate. For example, they'll multiply this one by 5 and get that correct, and they'll forget this number. Like they won't take that 5 all the way across. And so whenever they get down to the end, they're missing some things. Here, I think they would pick up on it pretty easily because we don't have enough. The carbons would kind of stand out if you only had 1 or 2 CO2s. But the waters, a lot of times the waters are what give people headaches. So then the next one, we have lots of things to multiply. We take 2 all the way through, 10 electrons, 16 protons. We get some pretty crazy numbers, like large numbers, like 16. 2 permanganates, 2 manganese ions, and 4 times 2 gives us 8 waters. So we've multiplied everything through by 2, and now we can get rid of things that are on both sides, like the 10 electrons. So add those together, and this is our final balanced redox reaction. And the charges should still balance because we multiplied everything by whole numbers on both sides. We add them down. So we could check our charges, 16 plus, 2 minus, and then the 5 times 2 minus would be -10, and then on the right we have +4. So notice it doesn't go down to 0, it just goes down to +4. And we check the atoms, 16 hydrogens on both sides, etc. So everything balances out. And so we checked our work. And then this is the N in the Nernst equation. So if we did the Nernst equation with this reaction, not only do we balance it, but we now know what to use for N in that Nernst equation. Now, in terms of calculating cell potential, we can look at that oxidation reaction. We go find the cell potential in the table here. It's minus 0.49. And then we change the sign because we flipped the reaction. And that's what that clockwise, pairwise, the lower one is the one that's flipped. And so we change the sign on that potential. But here's the thing that people mess up. They incorrectly multiply those potentials by the 5 and the 2. And so we do not do that. We do not multiply those half reaction potentials when we multiply the reactions. Now that's a little difficult to understand, but think about it. We're adding capacity, not voltage. So this would be like adding, if we had that oxalate reaction, let's say that was a battery. This would be 5 batteries in parallel. So we're not changing the voltage. It's still whatever voltage, but we just have more oxalate ions and more electrons, but they're not being pushed any harder. So if we were to multiply the potential, that would be like putting these batteries in series where they're stacked on top of each other, but that's not what's happening here. So this is just giving us capacity. And so that's just what I'm saying. You flip the reaction to make an oxidation, then you flip the sign on the reduction potential, and then you add them down. So this is a 2-volt cell. Now, this is a little bit an addition onto what you've learned before. I don't think they teach line notation in the freshman course. And this is how it's written out. So it's always anode first. And then these little vertical lines represent junctions. And so there's a junction between the solution and the electrode. And so there's a line there. And then if there's a salt bridge, there's a couple of lines in the middle to indicate a salt bridge. So there's a junction between the solution and the beginning of the salt bridge. And then at the other end of the salt bridge, there's a junction ending the salt bridge and going into the next solution. And then there's a junction here between the reduction reaction and the cathode. And then it's always written in this order: the anode first, the oxidation reaction, the reduction reaction, and the cathode. And this is a shorthand, so a lot of the things are left out. Okay, and I know that's frustrating, but we'll see. So here's an example. Here's the cells shown so far. This was a copper. Actually, instead of the zinc, I use a silver in this example. So this is the copper solid electrode and the copper 2+ ion, the silver ion and the silver electrode. Here's the manganese and aluminum cell potential. So you look at this and you say, well, how's this reaction being described? Well, the manganese solid to manganese ion, that's an oxidation reaction. So you would write it out with the manganese solid going to manganese 2+, and the other is a reduction. So it would be aluminum 3+ going to aluminum solid. Now here's an example with non-metal reactants, kind of like that oxalate and permanganate reaction. Here's a chlorate and perchlorate reaction with permanganate and manganese ion, and with platinum electrodes. And so these reactions are taking place at the platinum electrode surface and sending the electrons through the circuit. And so here's an example calculation using line notation, but we kind of got behind from this morning's earlier activity. So I'll try to finish this up next time, and that way we don't try to we don't go too far over. We're already about a minute over. And so next time we'll start with line notation and calculations.